Hello world, and welcome to another Python tutorial series. This time we're going to be looking into uh, the minimization function called the Broyden method, and going so deep into it as to even approve upon the version that you would tend to find in something like NumPy. But the first step of that is to just do the Broyden method and explain what it is and everything of that nature. So that's what this video is going to be focusing on. So before we get into all of that explicitly, I'm just going to import a bunch of stuff we'll need. Heck, I'll even copy and paste it. Okay, so as you can see here, we have Jax, Jax NumPy, Jax config, SciPy optimize. Most of this stuff is somewhat intuitive of why I would need it. Jax is a system for automatic derivatives, and it helps a lot with different types of calculations. NumPy just being a general data analysis thing. Jax using that special technology within there. And then minimize function and things like that. And roots, that's what we're focusing on. And then here we're changing the specification to 64-bit rather than 32-bit, just to be more precise with these exact methods that we're dealing with. So, in order to have, since this is minimizing functions, you need to have a function to minimize. So, I have one right here. I'm just going to copy and paste this one again because it's not that important. Just defining a function x and returning a JMP array. That's just some random stuff here, but notice that it's based on a vector x in its first element, and then x and its second element with indices 0 and 1. And there's some pretty weird stuff going on of a sign in there, a cube of the sign, a -1 out. And then again, we have a different function here. Is a list of two functions where we have another thing with the two values and a cube in there. All just to make things nice and complicated. We have two equations and two variables interacting in complicated ways. Okay, so the first thing that we're going to do is just find out what the Broyden's method is all about. So the Broyden's method is somewhat simple in its single variable form. It just says that the derivative of a function of x is approximately f of x minus the f of the x before. This isn't a discrete system of sorts, and over x minus the x before it. And then to get the next x plus 1, simply have x minus the function over the change in the function. This is all basically just the Newton's method. Things get slightly more complicated when we're dealing with multiple variables like we are. And the first thing that we're going to notice pretty quickly is that we end up using this thing called the Jacobian, which is the derivative of each equation for each variable. And so that's the first thing we're going to do. And so first we have to just start with some initial guesses for x, which for our sake is just going to be some zeros. And of the right dimensionality, which is 2, just a vector of 2 zeros. And then we're going to find the Jacobian to be Jax dot Jacobian function of x. And with this may seem pretty simple. That's because it is. Jax is pretty powerful. And then for the sake of brevity, f is function of x, which we will use for the actual method. But okay, now we have the Jacobian and the starting x's, and so we're going to have to do some loop to solve things, right? But what are we doing? So scrolling down, but not too much because there's something I want to talk about. So essentially, the next value in x is determined to be the previous one minus the inverse of the Jacobian times the f of x. And so one way, so to start the loop real quick, let's just do range 20 just to make sure you don't get too many steps. The xp, which would be like x n plus 1, so x pluses, the way I'll say it, we're going to do something called linear algebra solve of the Jacobian and negative f, which is effect plus x, which is effectively what I said before, just with the variables rearranged in a certain way. But it's effectively getting at a way to have the inverse of the Jacobian and get the x plus, really. And so a useful variable that we're going to need, real quick. So what's going on here is that we get this, and then for the next time around, we're going to need a new Jacobian in order to do the loop properly. And so we have this formula here for the Jacobian, and these double brackets are the norm. And so we're going to need the change in x as well as, I thought I had I lost my notes, but going to need the change in x, and that's about all we need to plug everything in. Now, this part here, this minus this, this can be simplified. I'll explain in a moment. So let's get that change in x, xp minus x, cool beans, and then fp is the f at this new x. And then for the sake of the loop, I'm going to redefine things really quickly. F equals fp, x equals xp, so that things can start all over again. And so that we can see what's going on, we're going to print x and fp. And then we're going to have, in order to update the Jacobian, it's my same form for a second, but I'll type it out real quick. We'll have new Jacobian equals the previous one plus JNP outer of the new f of x and times d of x, all divided by JNP ln alg dot norm. That's the thing I talked about before, the norm of dx squared. All right. And to make sure this doesn't run forever, I'm gonna have a break in here. So if, and this one's gonna be very intentionally made, JNP ln alg dot norm of fp is less than EPS, the thing we stated before, then break. All right, so essentially what norm is the average of a vector or matrix, effectively. It's just another fancy way to say it. So if the function we're trying to minimize to 0 gets very, very, very small, then we're done. We got it. Cool beans. And this right here, what I was meant to talk about before, this is a simplified version of this. We have the norm of x squared at dx squared. No changing that. We have the Jacobian before. This stuff, I won't do it now because I'd have to write out all the work, but this is essentially just the outer, which is simply the product in a certain sense of these two vectors in this manner of those aspects. So hopefully it runs out. Let's see what I got here. Oh, I always forget. You guys know me. I always forget the colons. I might not be able to put the EPS like that. Maybe I have to do that. What is going on? Oh, I did it again. No colon. Jax.numby has no attribute linAtch. Yep, that's because it's linAlg. We're cleaning up the errors and getting the final answer. So, what do we have here? We have the printed x and fp, and they're two-dimensional because we have the two equations and the two variables. And so the value of x's that we're ending at is around here. And you can see it's very, very close to 0 with the e to the negative 14s and e to the negative 15. It works. But for the situation is that this JNP solve is a very expensive function. We're doing it multiple times, and for increasingly complex systems, such as ones with hundreds of variables or very complicated equations and things, it's going to be very slow, and part of the point of coding is to get these things to go fast. And so, to help out in this regard, we're going to use what this Wikipedia page recommends, the Sherman-Morrison formula, to get the inverse of the Jacobian. Because since we need it in there, it's going to be very useful. And so what is the Sherman-Morrison formula? Effectively, it tells us that the inverse of A plus another matrix, inverse of that, the inverse of the matrix, and all this other stuff. But it does not have the invert. It cuts down on the computing time is the main thing of it. It gets rid of inverses along the way. You really only have to do one, and then it calculates the inverse for you. And these U and V's, we'll talk about exactly what those are in a second. So we're going to start a new thing where we define an actual Broyden formula. And so we're defining a function, Broyden, that takes in func, the thing we just made up before, x j equals none, but that, yeah, j equals none. This is the default for the Jacobian. You could enter it, but the default is that there is no Jacobian. Max iterations is 100, let's say, and verbose equals 0. Verbose. Okay. So we're gonna get the Jacobian real quick. So Jacobian of the function of x, and just a little caveat, if j is none, it is, so this is only needed if they didn't give us a Jacobian, but if they do, we just do j of x. That's all it is. And then we're going to need the first inverse, like I said. So j inverse is j and p dot linear algebra dot inverse of j. F is the function of x, just like we did before. And this time, instead of some arbitrary 20, for I in range max iterations, colon, I'm not forgetting it this time, xp, just like before, is, well, almost just like before. This time we're directly using the inverse of j, and we're not solving it along the way. So x minus j inverse, and then matrix multiplication, f. And then, just like before, I might even be able to copy this part. Ooh. These 4 basic functions. Put them all in the right space to all be in the loop. And then this little thing says that if verbose greater than 0, which means if they changed it so that they want to see the results along the way, that's what verbose means, then print x, f, cooties, and then again, very similar thing. You know what? I might just copy and paste again. Doop. Doop. If the function approaches 0, then we're done. We've completed the task. Now to get to the fancy Sherman-Morrison U and V stuff. So U is going to be JMP expand dims of FP to 1, and then V equals JMP dot expand dims dx 1 JMP 1 alg dot norm dx squared. And expand dims is just something to get the vectors in the right number of dimensions to do all of these calculations that we're going to do. And the Sherman-Morrison formula itself, J inverse equals the previous J inverse multiplied by U multiplied by V transpose, easy as that in Python, just .t, multiplied by J inverse again, but divided by 1 plus V dot t at J inverse at U. And we have it. Return x, f. Alright, does it... we're missing something. It's probably the colon again. Yep, always the colon. Okay, so let's use it. Broyden of the function func, and our x. Let's do some zeros again, because who has a better guess than just zeros? And shift enter. Takes a second. And uh-oh. Something's up. Let's run everything again, just to make sure. Not a number. Interesting. Let's see what we have. Everything. Just clean it all up just to make sure P function f equals xp, x equals xp. Verbose. You know what? Let's do it. Let's do verbose equals 1. What do we have? Okay. Oh wow. So it looks like it went through all 100. Oh jeez. How did it go? Oh wow. The numbers got giant for some reason. Why didn't they approach 0? That's an interesting dilemma. Just double checking everything I have according to my reference. J inverse. Oh, I know what I did. I didn't actually put down the Sherman-Morrison formula. I didn't put the, just because there's 2 J inverses in a row, I forgot to put the J inverse minus all the rest of it. So get that down. Enter this, should be pretty quick. Boom. And there we go. Just a few steps here. And we have a final answer with these x's and again these f of x's that are effectively 0. Okay, so that is the basic Broyden formula with the Sherman-Morrison formula intertwined, which is the norm, and later we'll be getting on to actually improving upon this.